are we?
What do we offer?
We cater to almost all the industries.
Electrical and electronic engineering,
computing and information technology,
mechanical engineering,
law and order,
Environmental science.
business administration.
We unleash your potential.
We are looking for niche communities
Of young passionate individuals.
Can be freshers to whatever the industry.
Might be interested in a particular field.
Don't worry, join us to find solutions for all your doubts.
We are Y2N Pro, young to niche professionals.
Good evening, everyone, and a warm welcome to our distinguished guests, members, and attendees. My name is Petu, and I am honored to be your moderator for today's session on the evolution of interior PM, synchronous machines, and control techniques for electric vehicle applications.
Electric vehicle workshop.
This session is brought to you by IEEE Y2N Pro collaboratively with the IEEE Industrial Electronics Society Sri Lanka chapter and the IEEE Power and Energy Society Sri Lanka chapter. Before we begin, I'd like to share a little about the Y2N Pro initiative. Spearheaded by IEEE Young Professionals Sri Lanka, Y2N Pro aims to provide a platform for young professionals to delve into niche technological domains through specialized workshops and courses. Y2N Pro has facilitated deep learning experiences, fostering expertise among participants in various fields such as biomedical engineering, power and energy, agricultural engineering, electronic design automation, and telecommunication engineering. Our goal is to improve the technical awareness required by niche communities and enhance the knowledge and skills of young professionals through hands-on learning experiences. The IEEE Industrial Electronics Society focuses on advancing the theory and practice of electronics, controls, communications, instrumentation, and computational intelligence in industrial and manufacturing systems. IES provides a platform for professionals to explore the latest developments and innovations in these areas, fostering a community that shares knowledge and collaborates on cutting-edge projects. The IEEE Power and Energy Society chapter of Sri Lanka is one of the most active chapters in the country. Their membership includes a diverse group of students, academics, researchers, and electrical engineers working in the industry. We are thrilled to have you join us for this exclusive online session. Today's session promises to be an enlightening and informative discussion on the evolution of interior PM synchronous machines and control techniques for electric vehicle applications. To begin, I would like to invite Mr. Kavinga Ekanayaka, IES Sri Lanka Chapter Chair, to deliver the welcome speech. Over to you, Mr. Kavinga.
Thank you, Patum. So first of all, I would like to thank the Y2N Pro team in initializing this session in collaboration with us, Industrial Electronics Society Sri Lanka chapter. So to begin with, I would like to welcome our distinguished guest for the session today, Professor Faz Rahman, who is a professor in University of New South Wales, Australia, and is a IEEE Life Fellow as well. And is a very prominent character in IEEE, very experienced and prominent character in IEEE and Industrial Electronics Society related fields. So then I would like to welcome everyone else who are connected with us today. So we have a pretty good audience tonight. I think all the electrical vehicle enthusiasts in IEEE Sri Lanka section, especially the young professionals, have joined with us today. So even though this is a welcome speech, I would like to do some appreciations. Initially, I would like to really appreciate the Y2N Pro team of IEEE Young Professionals Sri Lanka. So the students and young professionals are usually the very enthusiastic and energetic team in the whole IEEE Sri Lanka section membership. Professor, we have a pretty good young and energetic team who are always courageous to do a lot of great activities in Sri Lanka section. So this particular project is also one of their many projects. So young to niche professionals, so they want to bring up one niche area every year and conduct a workshop series so that other young professionals and students will learn a lot from that one. So for this one, it is really crucial to get experts around the globe to do this presentation. So we kindly reached Professor Faz Rahman, and he was really promptly responded back to us and like offered to help us with his prominent lecture. So this is not simply a webinar. This is a distinguished lecture under the IES Distinguished Lecture Program. So to give you a bit of an idea about that one, in IEEE, you have several technical societies. Like there are about, I think, many societies available, technical societies. For an example, Industrial Electronics Society, Power and Energy Society, Robotics and Automation Society, etc. So in all these societies, there is a distinguished lecture program available. So these distinguished lectures are usually like IEEE fellows and IEEE Life fellows who have achieved a lot in their respective areas, like Professor Faz Rahman. So they are really the core experts in the particular field in their respective fields. So when it comes to distinguished lectures, usually there are physical DLPs as well. But in case that we need to have more distinguished lectures, nowadays societies offer even virtual DLPs because the content is more valuable than arranging all other logistics. So that will allow us to have more distinguished lectures, reach into more distinguished lectures like Professor Rahman. And this is one of such opportunities that we have today. And as I mentioned, our young professionals team, also I would like to recognize the collaboration that we have from Power and Energy Society, which is always a sister society for us, Industrial Electronics Society, and also the support given by IEEE Sri Lanka section in mainly in the publicity related areas and all the advices that they have given to conduct this DLP. I would like to thank Sri Lanka section as well. Finally, once again, I would like to welcome you all. You are the most valuable people that we have today, the audience who are with us to witness this wonderful lecture. So I hope the electric vehicles is a hot topic nowadays, similar to the machine learning and all these LLM things. Electrical vehicles is also a very popular topic with all the energy efficient requirements, and all electrical vehicles are becoming popular over other like fuel enabled automobiles. So this will be a really good journey for all of us. So thank you very much, everyone, for joining us today. And back to you, Pathum and the team.
Thank you, Mr. Kavinga, for that warm welcome. Now, it is my pleasure to introduce our keynote speaker, Professor Faz Rahman. Professor Rahman is a distinguished academic researcher at the University of New South Wales, Australia. He serves as a professor within the School of Electrical Engineering and Telecommunications and heads the Energy Systems Research Group at the university. Additionally, He is a distinguished lecturer at the IEEE Industrial Electronics Society. Professor Rahman's expertise lies in drive system analysis and design, power electronics in electric drives, and motion control systems design. With numerous publications in high-impact journals and conferences, his dedication to research and teaching has established with numerous publications in high-impact journals and conferences, his dedication to research and teaching has established him as a leading figure in electrical engineering and telecommunications. We are honored to have him with us today to share his insights on electric vehicle applications. So, without taking much time, let's welcome our guest speaker, Professor Faz Rahman. Professor, the virtual stage is yours.
Okay, so thank you for the introduction. I remember what you said about me, but you may also know that I have organized many IEEE distinguished lectures in Sydney and in this region, including New Zealand, Australia, and then China and all that. So now I'm on the other end, that I'm having to give the DL lecture for the IES. Now, can I go? This presentation is about what enabled the electric vehicle applications to come of age, what stopped it for such a long time, and when it started, that means this EV revolution, what enabled that to happen. So it's a bit of a historical to start with, but the technologies involved behind the EV to be successful, and not just EV, but there are also electric trains and so on. So the technology behind that, I'll want to go over with you in the remaining time. So can I go to the next page, please? So in this page, we are looking at one of the first electric vehicle that was, I don't know why there is this, the screen has some double writings anyway. So could you go to full? No, you should press the full screen button here and then advance, sorry, and go to the next. Anyway, so go back one screen. Okay, I'll just briefly review the historical setting. What you see in picture was probably the first electric vehicle developed in 1932 by the Scottish inventor, and his name is Robert Anderson. He had this electric vehicle where you can see the battery under the seat, the slender electric motor, and the gear. The wheel has a gear, and then the motor has a gear, and they're engaging. You cannot see my cursor, can you? As I'm moving?
Not really.
Yeah, so without the cursor, it's also a bit difficult. Anyway, so let's move on. So anyway, this figure shows the first electric motor, so electric vehicle. And you would be surprised to know that electric vehicles outnumbered IC engined vehicles like petrol and diesel vehicles up until 1920. Even in 1920, the sales of electric vehicles were twice as many as petrol and diesel vehicles. But then the oil industry started to offer very cheap gasoline, and then the whole world moved to IC engine-based electric vehicles. So can I go to the next page now? The next page, please.
Yeah.
So,
Yeah.
Because I don't have full control on the screen. Okay, so what do we need to have a successful and viable electric vehicle? You need high electric motor of high power density, which is item number 1. And the motor must have a very high field weakening range. I'll talk about what is meant by field weakening range a bit later on. And then the motor must have very fast integrated sensors and controllers. And then the converter has to be very fast and high bandwidth, which is usually obtained with high frequency integrated converters that are now available in the form of IGBT and MOSFET inverters and so on. And then high energy and high power density batteries. As you may be well aware that the high power density and high energy density batteries are still undergoing much development. I cannot say that it has seen the full development yet, but every day you find in the news that the solid-state battery are coming, the range is coming up, and so on. So the battery chemistry and the battery other properties of battery like energy density, power density, battery range, battery life, energy storage, total energy storage, and so on. So those are increasing virtually every day, or getting better virtually every day. Can I go to the next page now? Now, if you look at this figure, this is how the electric vehicle industry is traveling. You can see some fast growth rate. If you look at the percentage numbers at the bottom, you can see that growth rate have risen and fallen and risen again and so on. So it is going through quite a bit of change, but the growth rate now is 35%, which is a bit lower than a couple of years back. But as you can see from these numbers change with many things, all right? If the new batteries become successful quickly, then these numbers will go up very quickly as well. So the trend of increase of electric vehicle sales is very high indeed. You don't see this kind of growth curve in other areas. Electric vehicle industry now is having this growth. So can you go to the next page, please? Now, the total, in order for the world to go to fully electric vehicle, which some companies are saying they will convert all their vehicle manufacturing into electric vehicle making by 2030 or 2035 or 2040 and so on. Most manufacturers are committing to not too distant future where all vehicles will become electric vehicle, and that will need about 300 terawatt hours of annual battery production, which are we are nowhere near that. but the way things are going, we should arrive there in not too distant future. This page mentions a few developments like what Volkswagen are doing in terms of bigger factories producing electric batteries. So let's go to the next page now. Now, here is an example of the other end of electric vehicle. This is an industry in Sydney where very large trucks, 500 kilowatt electric vehicles are being produced. Now, these trucks started life as IC engine powered like diesel vehicles, but these are being converted. These have been converted, are being converted into electric vehicles. So it's 600 kilowatt hour batteries, 500 kilowatt IPM SM, and so on. And these trucks travel from port to mines, and so that their route is well defined, and they simply change batteries every 500 kilometers. So they go to the service station, and then they change the battery within 10 minutes, and then they can go again. All right, so no need to charge batteries for such large electric vehicles while the driver has to wait. They simply change the batteries to the whole battery set, which is 600 kilowatt hour. Anyway, this is one trend that is happening worldwide, not just in Australia. Can I go to the next slide now? Now, on this slide, I'm showing what I mentioned some time ago, that the electric motor, which have to be the main traction motor in an electric vehicle, has to have a high field weakening range. All right, if you look at the torque speed characteristic of that motor, let's say up to 2,800, what you call it, the flat torque, and 2,800 is the base speed. And from 2,800 to 14,000, which is a range of about 5, so you need that 5 to 1 field weakening range where the power remains constant and the torque falls as the speed increases beyond 2,800 RPM. So on the sliding down curve, at every point on the curve, the product of torque and speed, which is power remains constant. And the speed range, which is 2,500 to 1,000 to 14,000, is about 5. And electric vehicle need that kind of constant power range. Up until recently, such power range, what we call constant power speed range, no electric motor could produce such high power range, constant power range, over which the power will remain constant and torque will fall with speed in a way that the product of torque and speed remains constant. So this kind of motor has only recently been in the last 10 years or so. All right. So that allows the electric vehicle, that is one of the cornerstone for electric vehicles to be successful. So we call it wide constant speed power range, or CPSR, which the motor must have, but that's for operational reason. But apart from that, the motor has to have very high efficiency, very high power density, very low cogging torque, very low torque ripple, and so on. So those are other characteristics that the motor must provide. Now, the motor that provides this kind of characteristics in terms of efficiency, CPSR, cogging torque, ripple torque, this kind of, and to mention power density. So this kind of attributes are now being offered only by the interior permanent magnet synchronous motor. Induction and DC motors cannot match such characteristics. Next slide, please.
Professor, can you try like moving the slides from your side? I have given the control to you. Can you just try it?
No, it doesn't move.
Doesn't move, right?
Right.
It works. It works. It works. Yeah.
It does?
Yeah, it does.
Okay. Okay, so this is the torque versus, oh, sorry. I'm too far ahead. So I'm now showing slide. Sorry, next one.
Right.
I'm not sure which slide number is this.
8. We can see 8.
Slide number 8. Okay. So you can see that the torque speed characteristic and the 5-to-1 constant power speed range. Now, in a normal vehicle or IC engine vehicle, the torque speed characteristics are the inverted V-shaped blue curves. All right. So at every gear change, the torque speed characteristics move up or down according to where the motor, at which speed the engine is running. And then we emulate a wide torque speed characteristic from the IC engine. But that means that we need to have a large number of gear changes. Here I have shown 1, 2, 3, 4, 5, 6, 7 gear changes. High performance motors can have up to from 8 to 12 gear changes. All right, modest cars have only 4, but those are very modest cars, don't have very high performance. So electric machine, the IPM motor, IPM synchronous motor, can produce this solid black line torque speed characteristics without having to without having to have any gearbox. All right, no gearbox is necessary. So the motor itself is inherently capable of producing high torque at low speed. And then as the motor speeds up, the torque falls. All right, this is the maximum torque. The black line shows the maximum torque demand on the vehicle. So the maximum torque can remain high up to omega B, the base speed, and from there on, it will fall inversely with speed so that the product of torque and speed remains constant. So this characteristic, the solid black characteristic, is obtained only by the IPM SM now without requiring any gearbox. All right. And at the same time, the motor can produce a high instantaneous torque at low speed given by the red dotted line. All right. Which internal combustion engine, IC engines, can hardly match. All right. Because all inverters and motors can have short time duty ratings of twice the rated power or twice the rated torque or more, even more. Inverters can have capacity of 2 times or up to 3 times over current for a very short time. Okay, so an inverter IPM motor drive can also give you this high low speed torque, which can give a lot of acceleration to the drive. So in other words, the drive performance becomes like a sports car, right? Very high torque at low speed, very high acceleration because of the red characteristic that the IPM machine can provide. So I'm now trying to go to the next slide. I have pressed the button for that. Nothing seems to be happening.
Yeah, maybe I'll do that. Okay.
Okay, so in this page, these are some examples of where IPM SM machines are being used. Virtually all electric vehicles now have IPM SM or PM synchronous machine because of what I just said before in the last slide. So next slide, please. So the outline of this presentation is therefore to show you what developments have taken place on the motor side, and then what developments have taken place on the control side of this motor. I have not included any developments in the inverter side. Inverter side has also undergone quite a lot of development, but the development that we required for electric vehicle existed more than 5 years or more than 10 years ago, as far as the inverter is concerned. So I'm focusing mainly on developments of the PM motor and the control system that is required for electric vehicles. So next slide, please. Next one. So this is part one, is the recent developments in electric motor. So if you, I'm not seeing the whole screen. I think something below I'm not being able to see. I don't know why. Can you reduce the no, sorry. That page that you were showing, there was a sizing equation here. Why am I not being able to see that? Oh. There was an equation. There was an equation here. I don't know why. Okay, so the machine has to have high efficiency, high agar flux density, and low diameter, the minimum diameter and minimum length, so that it can be housed within the electric vehicle and so on. So the density of the machine in terms of power to volume ratio has to be very high. And that equation that I don't see now, why is it missing? I don't know. So that equation showed what parameters we normally have on the mechanical side in terms of dimensioning the machine, and then and then later what parameters we have in terms of the electromagnetic part of the machine. So can I go to the next slide now? I'm not, I think for some reason, the presentation is going outside the screen, at least on my screen. So I don't know why. You can now go to the previous slide, please. Okay, so IPM machines or IPM synchronous machines have to have all those attributes that I show under dot points, all right? And then the trend have been to use IPM SM, which I showed before, all right? And then over the right-hand side, I have shown you a typical torque speed curve of a IPM motor drive for an electric vehicle, which produces about 300 to 400 Newton meter of torque below base speed. And from there to top speed, which is more than 5 times or about 5 times, that's the torque speed characteristic. And you have to have efficiencies as I have shown with those arrows. Okay, the curves, the curves and the colored parts belong to various degrees of efficiency when you operate the machine at various power levels. All right, if you operate on the envelope, then as you can see that the efficiency is of the order of 95%, or around between 90 and 95%. All right. So this is what the motor efficiency we can now obtain. Now, the curve below that, I saw the material that we use, all right, for this permanent magnet machine. These are rare earth materials called neodymium iron boron, but it has to include some other materials like dysprosium or cerium, which increases its thermal withstand capability. Neodymium by itself doesn't have very high thermal rating, all right? Its Curie temperature is about 120 degrees, but with dysprosium and cerium, its temperature, the magnet temperature characteristic can go up to about 300 degrees Celsius. All right. So that's the advantage of using this other material with neodymium iron boron. But dysprosium and cerium, these are also quite expensive. The price comparison with respect to gold are shown here, but these materials are quite expensive to enhance the characteristic of the neodymium material, iron boron material, but industry is steadily being able to use other materials which are cheaper. Okay, so all in all, the neodymium iron boron material, which is rare earth, have been enhanced in terms of thermal capability by using some other materials which are also rare earth, but fortunately the industry has found, or the material designers have found other materials which are not used, which do not need to be used in high concentration. Next slide, please. the blue line, when we design an electric motor or high performance electric motor, we first select the material. All right. And I just mentioned to you just now that the material that we use is on the BH characteristic plane. The material lies here. All right. Which is very high coercive force and quite high remnant flux density. The BH curve I'm showing on first quadrant, but it actually exists on the second quadrant. All right, so we use this material, which is neodymium iron boron. For some reason, all the legends are not coming when you are using your display. But anyway, and the blue line is the characteristic, BH characteristics of this material on the second quadrant at 20 degrees. All right, but machines have to operate at higher temperature. All right, so at higher temperature, the BH characteristic will fall. And then at even higher temperature, 150 degrees, the demagnetization possibility becomes real. All right, the magnets can become demagnetized by the current that flows in the stator winding. So this is quite unhelpful if the machine goes machine B field or H field rather, or H and B field go beyond this point to the left. Then the machine becomes, then the magnets become permanently demagnetized, and then the machine becomes useless. Okay, so at first we have to choose the material, which is IPM. Then it has to have some additives like dysprosium or cerium and things like that, materials like that, so that the temperature characteristics becomes close to the blue line up to quite a high temperature, higher than 150 degrees C. All right, so that problem has now been solved, and we get very reliable operation of the machine up to the full loading of the motor. So the first step in the design of the high performance machine is to find the material, which is neodymium iron boron, and to have additives to it so that its characteristics is close to the blue line for all temperatures. Okay, and then let's go to the next slide, please.
Oh.
Then we look for, sorry, next slide, not so much so far. Yeah, just the next one here. So up to about 15, 20 years ago, most electrical machines had distributed winding, where the A, B, and C phase produced windings were distributed all around the stator slots. Okay, I think most of you would be familiar if you're an electrical engineer. The distribution of the winding is all around the sphere of the cylinder in the slot in the cylinder cylindrical structure of the stator. But recently, we have what we call concentrated winding or fractional slot concentrated winding, which is defined by slots per pole per phase, which is called SPP. All right, if you divide by the number of slots by the number of poles, normally 4-pole machines or 12-pole machines or 18 pole machines. So we know the number of poles in order to determine the base speed. And then we have the phase, usually 3 phase, all right? And you can see from the diagram on the right that A, B, and C windings are in localized slots, all right? A winding is in the left and on the right slots. B winding is on the top and bottom slides, and so on. So the slots don't overlap, all right, which are called concentrated windings. Now, normally, if we have concentrated windings, then we get some advantages. Can I go to the next slide, please? Now, these are the slots, and the windings are concentrated, as you can see in this diagram. All right. The slots and the windings can be modular. That means each pole can come with its winding. All right. This is not how the distributed windings are made. This is called fractional slot concentrated winding design. So in this design, the stator poles and the windings can be wound separately and then stacked together. Okay. Now, this has the several advantage. One is that we can do modular design. All right. The pole and the winding can be designed or can be manufactured separately, and then they can be put together as shown on the right-hand side. Okay. Now, this kind of concentrated windings also give you high inductance in the stator windings, okay, which means that the inverter, the motor drive has a high fault current rating, or the fault current can be tolerated better because of the high inductance. The inductance will slow down the rise of current if the wheel, for example, is suddenly stuck. All right. If the rotor is not rotating, there is no back EMF to limit the current. But if the machine has a high inductance, the current will take time to rise because of the high inductance. And by the time the current can reach disastrous levels, there is enough time for the control protection circuit to take some measures to limit the current. So that is one of the advantage of fractional slot winding. Can I go to the next slide, please? Now, as you can see here, the example at the top left hand, the example at the top has several motors, IPM machine with concentrated winding. As you can see, the windings are put together on individual poles, and then they are assembled together. All right. So, in other words, the stator parts come in parts. All right, in many parts, and they're simply put together. Now, in one of those slides at the bottom, which is the right-hand side, we have the magnet. All right, you can see here the magnets are in the rotor, and the stator is on the left-hand side of the Toyota Prius, which is 2010 and 2017 design. So you can see that the magnets look like a V. All right. So I'll talk about that a bit more later on. So this is the way IPM machines are being designed. The magnets in the rotor, and the magnets have certain shape, in this case V shape. And if you look closely, you will also see that there is a bit of iron between the two parts of the V, and that iron has to be very carefully dimensioned so that the machine has the proper field weakening capability. So next slide, please. Now, I have already discussed some of this, mentioned some of this before. The FSCW design, the fractional slot design, can give you high field weakening range. All right. Cogging torque are quite small. All right. Can be made very small by using a very large LCM, the least common multiple between the number of poles and the number of slots. Okay, it's all in that number called SPP, which is slots per pole per phase. Okay, now the concentrated winding doesn't have the end winding. Distributed windings, the winding at the back of the cylindrical body has to travel rotationally, has to travel in an angular direction before entering the next slot. All right. So that is an overhanging part of the winding, which serves no purpose. Okay. So in terms of torque production, so that means that the copper length is reduced, the length of the winding is reduced, and as a result, copper losses are also reduced in this machine so that the efficiency can be higher. I have mentioned the reduction of short circuit current because of the high inductance that is achieved through concentrated windings, and the fault tolerant capability that comes from that, and also from the fact that the windings are not covering each other. So the voltage, various winding parts are not coming under various, excuse me, are not coming under different voltage gradients, all right? So there is less chance of short circuiting or insulation fault in the FSCW machine. And because of absence of overhanging design, overhanging winding of the distributed winding, the motor becomes of compact size, and that also gives you high power density, which is required for electric vehicle because the space under the vehicle is very limited and have to be used and therefore expensive and has to be used with a lot of efficiency. So next slide, please. Now, then, so after the stator design comes the rotor design. I have mentioned V-shaped winding, all right, spoke-shaped winding, and then multi-layer winding. There are several multi-layer can be V-shaped, and then combination of V and spoke, and so on. There are many geometries possible, all right? But once, and in the last few years, all these geometries have been studied extensively using finite element method of analysis, and then various configurations of the rotor or various designs of the rotor poles have been optimized, all right? What you are seeing in this paper or in this figure, you can see that one magnet here, another magnet here, let's say north here. So this is the North Pole, all right? And on the other side are the South Poles, all right? Now, on the machine with two V's, two layers of V magnets, the total flux can be increased by two sets of magnets, all right? As in the multi-layer horizontal flat rotor, flat magnet winding, which is the fourth one, all right? And the spoke machine, for spoke type machine, the magnet is placed radially on the rotor, all right? But it has to have some non-magnetic part, non-magnetic area at the top and at the bottom of each magnet, so that there is no local short circuit of the magnetic field. Now, the very last one is the surface magnet motor, where the magnet is placed on the rotor surface, but that machine has no application in electric vehicle because it doesn't give you any field weakening range. So anyway, so the most popular design now is the V-shaped magnets that I can see. All right, various manufacturers like Tesla and Toyota and so on, and Honda, they have adopted the V-shaped magnets. All right, whereas some German manufacturers like BMW has adopted the multi-layer V and flat-shaped magnets. Okay, the next slide, please. Now, then the geometry optimization. The geometry that you had seen in the previous slide, both in terms of the stator and in terms of the rotor, the placement of the magnets, the thickness of the magnets, the breach between the two sets of magnet, which is the middle part of the two sets of magnets. So various dimensions are there. Length and separation at the outer part, at the top of the magnet, separation at the bottom of the magnet, separation between the magnets, the iron bridge dimensions, and similarly for the stator, teeth and slot and so on. There are so many dimensions. So we need to have the geometry optimized, which is the last part, okay? And in the geometry optimization, we first decide what attributes of the machine we want to have, all right? What inductance we require, which will give us sufficient fault tolerant, all right? What should be the efficiency of the machine? What should be the low torque ripple? What should be the power factor? What should be the torque density or power density, and so on? And what should be the field weakening range, whether we are meeting the 5 times or 4 times or 6 times the power range from base speed to full speed. So all kinds of attributes or optimization goals we can define, all right? And then if for each of the design or each of the dimensions that we select, we calculate all these parts or all these figures and see whether the machine is within that characteristic, all right? I have listed a few here, but there are also other like field weakening range and so on, which I have not mentioned here. So anyway, so this geometry can be varied bit by bit, and these figures can be found through finite element analysis, and then finally we decide on a certain design that meets all the specifications. Normally it takes quite a long time. One mechanical dimension change and the effect of that to all of these can take several days on a high performance computer. All right. So anyway, so this is the design process. Can I go to the next slide, please? So these are some typical machine design. As I said, the V-shaped is the V-shaped and the multi-layered design, which are item D and E, and also these are the two most favored. The multi-layered design is favored in Europe, and the rest of the world are using V-shaped magnet. Next slide, please. Now, the optimization process, for example, the Freedom Car 2020 specification define these specifications, all right, that a motor must meet. And then we used MATLAB, then finite element analysis and optimization procedures for every dimension change to see if these characteristics can be made. So these were goals set for Freedom Car in USA, Freedom Car 2020. All right. But one of motor that we designed in 2019 or came up with in 2018 and 19 meets these characteristics, except for the power density. All right, we are slightly below the power density. And I'll show you that design further. So can I go to the next stage? Next page. Next page, please.
This one?
Yeah. So, this is the thermal design. Depending on the magnet and the ion dimensions, we can create a thermal model, all right, in terms of thermal resistance, thermal capacitance, and so on. So that is an RL network or RC network, which we can establish for the thermal model of the machine. And then we solve for the thermal model to see if the power, what will be the power loss. All right. And then we determine from the thermal mass what will be the temperature range or rise. And if the temperature rise will go outside the magnet temperature. All right. Normally the magnet temperature is to be kept within 100 degrees C. So not only that we need the other electromagnetic performance, we also have to have a thermal performance. Excuse me, sorry. So this is another optimization program that has to be undertaken. And yet a third optimization program is to check the mechanical dimension. Note that the magnets are in slots in the rotor at very high speed. There are parts of the metal in the rotor which may not withstand the high centrifugal force. All right. And the rotor may deform as a result of that. So one has to make sure that the thermal, not only the thermal and electromagnetic performance like efficiency and power density and torque production, torque ripple, and so on are okay. We also have to know that all parts of the material of steel in the rotor is well below the mechanical strength of the material. All right, and it has to be good. The material strength, the margin between the allowable maximum strength and the allowable strength should be such that the motor mechanical integrity should be good for 20 years or so, or fast acceleration, deceleration, and so on. So that's another optimization that one has to undertake. Next slide, please. So these are one design reported in this paper, which is called delta-shaped magnets, all right, which is a rotor which was optimized, and their goals was to extend the field weakening range or constant power range, minimize losses, reduce torque pulsations, reduce harmonics in back EMF so that the torque ripple is contained, and so on. So the delta-shaped magnets look like very promising in 2010. However, I have not seen any use of it in any industrially produced electric vehicle yet. All right. So, which I'm mentioning this, I'm just bringing up this design just to show that there are so many varieties of electromagnetic design that have been used or that has been tried with a view to improve and meet the performance requirement of electric vehicles. Next slide, please. Now, this is the Toyota hybrid vehicle and Toyota vehicle. This is the Toyota vehicle price motor characteristics, which is used for hybrid vehicles. All right, doesn't have the full 5-to-1 speed field weakening range because it is only used for duty to accelerate from 0 to full speed. All right, not for field weakening. একটু পরে দেরি আছে আমার এখন আধা এক ঘন্টা লাগবে sorry next slide please. Now again some examples of multi-layer and V-shaped magnets or V-shaped magnets in the rotor of industrially used electric vehicles. Next slide, please. Now, this is a electric IPM machine, IPM SM, which with a SPP of 3/7 that we designed in our labs in 2012. The machine gave, in those days, our focus was to get high field weakening range. All right. So we got very high field weakening range, but at the same time, we didn't get many other requirements. Okay. But at least it was clear that the V-shaped magnets, as you can see here in the cross-section diagram below, the V-shaped magnet produced high field weakening range. But because we use 3/7 as SPP, 18 pole, 14 slot machine, there were low order harmonics of torque which needed the D and Q axis shift when the machine was operated at high speed. That is not attractive at all for control purposes. That becomes the control very complicated, and that makes the control very complicated. Anyway, later on, after we understood the role of the V-shaped magnets, we then embarked on other designs. I'll show, if you go to the next slide, please. The next one. This is the torque character. This is the ripple torque of the machine, which is 3/7 SPP. All right. And then finally, in 2000, we published into 2021, but we developed this machine in 2018. And this is called a Y-shaped magnet. You can see that the rotor magnets have an Y shape. All right. So we call this V. This is the left-hand side is V-shaped. The middle is I-shaped or the spoke shaped. And the marriage between the two is called Y-shaped. Okay. So this Y-shaped motor allowed us to meet the Freedom 2020 specification in 2018, except for the power density. And we believe that the power density could not be met because our machine was a small size machine, only 2 kilowatt. If we made it to higher capacity, then its power density would have been higher. So anyway, if you go to the next slide, please. We can see some characteristics of the Y-shaped rotor. You can see that the spoke type motor has this back EMF characteristic, which has some ripples. All right. But our Y-type motor has higher fundamental back EMF. All right. So you can expect higher torque production for the Y-shaped motor. So this is a comparison between V-shaped, spoke-shaped, and Y-shaped motor. All three of them optimized using the routines that we discussed before, or that we indicated before. So the Y-shaped motor gave us the highest back EMF, which means high torque. All right, go to the next slide, please. And it's cogging torque, and this one is cogging torque, is marginally higher than the V-shaped and spoke type motor. All right. Spoke type motor is also 0.8 Newton meter, whereas the Y-shaped motor gave us a cogging torque amplitude of about 0.8. So similar. Only the V-shaped magnet motor get us cogging torque. When I say cogging torque, this means the torque produced by the shaft when it is rotated mechanically over a certain number of degrees. Okay, if there are magnets in the rotor, you would expect the magnets to lock in with the stator poles. Okay, so that is called cogging torque. So that torque should be as low as possible, because cogging torque produces losses and produces no useful gives no useful torque for the operation of the vehicle. All right, so the Y-shaped magnet has high back EMF and cogging torque comparable with the spoke type motor. All right, let's go to the next slide, please. These are torque ripples. Again, the Y-type rotor, while it is running, because of its low back EMF, because of its high back EMF, and the slightly higher ripple, gives you a bit of about the same, slightly higher ripple torque. That means the torque produced by the torque variations at different angles. The motor produces different torque at different positions. Ideally, it should be very smooth, but that never happens in any electrical motor. And these torque pulsation are quite low compared to what many existing motors has. Okay, so you can see that the V-shaped magnet has 7.8% cogging torque, whereas the Y-shaped motor has 2.97% ripple torque. Sorry, not cogging torque, but ripple torque. Next slide, please. These are inductances of the machine and the flux density distribution in the air gap and so on, so which have been shown in another form in the previous slide. And we also see that the back EMF goes up linearly with speed, which is obvious, but the Y-shaped motor give us higher back EMF compared to spoke type or V-shaped magnet motor, which is the reason for its higher torque production or torque density and lower ripple in terms of percentage. Okay, next slide, please. So this is the top one. Again, the V-shaped magnet it shows higher torque speed range. All right, with the required 5-to-1 field weakening range and higher torque overall speed and so on. Okay, so compared with the two other types of motor, the Y-shaped motor has given the best characteristics, and we have produced the efficiency map of the vehicle, of the motor. That means what will be the efficiency of the machine at different operating speeds and different operating torque. All right, so that are shown for the three different motors in the three curves. And as you can see, if you overlap these three curves, which will become very complex, but a complex figure, but you can then determine that the Y-shaped motor gives you better efficiency, higher torque, and so on compared to the other two. So we have this Y-type motor currently patented in Australia and USA. And we are hoping that it will be taken up by some vehicle manufacturer sometime in the future. So next slide, please. This is a comparison between Toyota motor and our Y-shape for similar power range, or for the dimensions of the, for similar dimensions of the Toyota Prius, okay? And we can see that our motor is a little bit better than the Toyota motor. Now, let's go to the next slide, please. So this is the summary of the IPM motor development. The designs are targeted for to meet specific specifications. The designs can now be thoroughly checked by using multi-objective optimization process, advanced optimization techniques that I have just only mentioned in this presentation can lead to novel designs. Our Y-shape motor is, we consider to be such a novel design. All right. So because the designs are still, various companies are coming up with various types of design. So off-the-shelf design, like you buy an induction motor for an application from the shelf, off-the-shelf IPM machine are still not possible or are still not available. Off-the-shelf machine will probably take still a few years to settle down. That means everybody will agree that a certain design is the best and everybody will use that design, and there will be no other requirement to check any other design. Okay, so that stage hasn't arrived yet. It will probably arrive in a few years' time. So that's the summary of the motor development. So there will be no problem with equation presentation. I didn't realize that the PowerPoint presentation at your end may also require the equation. Yeah.
How about this one, right? Professor, can you see it clearly now? It's much better, I guess. Yeah.
Okay, so shall we go through it?
Yeah, please go ahead. We can quickly go through it. Yeah.
Now, this is the motor model. All right. In order to control a motor, first of all, we need to have the motor dynamic model, right? And what you are looking at is the motor dynamic model representation in terms of voltage, D and Q axis voltage, D and Q axis currents, D and Q axis fluxes. Okay. So that requires dq transformation of the motor equations. And then you have the voltage, stator voltage equation for the D axis given by the top equation on the left. And the below that is the Q axis voltage equation. All right. The rotor magnets will produce a flux linkage lambda F, but the stator current ID will also produce a flux linkage in the D axis. All right. D axis is the magnet pole axis, and the quadrature axis is the axis at right angle straight. Okay. The current IA, IB, IC have ID component, which produces flux along the D axis, and IQ component, which produces flux along the Q axis. All right. So these the currents and the rotor flux produce the developed torque equation, which is the third equation from the top. Okay. Now, and then that torque has to be balanced with the mechanical torque. All right. So the right-hand side is the mechanical torque equation. So can I go back to the left-hand side again? Sorry. And then the total voltage is Vd square plus Vq square root over, which is this top two voltage equations squared and added. All right. And if you neglect the resistance, then the equation of the fourth line becomes the equation which is the 1, 2, 3, 4, fifth line equation. Okay. So this equation is the equation of a ellipse. If you recall the theory of ellipse, and IS, of course, is the total current, which is equal to root over ID square plus IQ square. So if you square it, it becomes ID square plus IQ square becomes ISM square. So total ISM is the maximum current limit of the motor. All right. So at any time, ID and IQ can have values which must be below ISM, all right, which is the maximum current limit of the motor. Okay. Now, based on this voltage equation and torque equation, as you can see for IPM machine, the torque equation is quite nonlinear. For DC machines and induction machines, you don't have the second part in the torque equation. The torque equation is nonlinear because of the product of ID and IQ. All right. In DC machines and in induction machine, this middle part, all right, which is LD minus LQ multiplied by ID IQ, that part is missing. That part doesn't exist. However, it exists in permanent magnet synchronous machine because of the geometrical shape of magnets in the rotor, inside the rotor. Okay, so this is called reluctance torque or torque due to saliency of the motor. Okay, this is a unique part of the IPM machine which can be exploited to increase the torque density and power density of the motor, and alternatively to reduce the size of the machine or reduce the volume of the machine for the same power. Now, based on these equations, we can do the control, which is the next slide. In this slide, we have the motor on the left, synchronous motor. The inverter drives the motor with currents IA, IB, IC, and the currents are resolved into ID and IQ by measuring the position of the rotor, which is theta E. All right, so ID and IQ can be regulated in a closed loop controller to control the torque. All right, remember the torque equation. Remember from the torque equation, the torque is produced by ID and IQ. So if you control ID and IQ, you control the torque. Okay. On the left-hand side of this slide, we have a voltage. We have a speed reference, what speed that the motor should run, and the speed measurement, which is omega. And then the difference, which is the error, goes through a speed controller and it produces a torque reference. All right. But remember, the torque is produced by both ID and IQ, all right, in a nonlinear way. So we have to have current IQ and current ID references generated from the torque reference, okay? And that was, in a sense, produced by the paper mentioned in the previous, or the guidelines for that, or analytical framework for resolving torque reference into current references were propounded by that paper, McMain and Johns, that appears in the previous slide. So let's go to the next slide now. So remember, ID squared plus IQ squared must be equal or less than the I max, all right? Stator current maximum value. So that is the equation of a circle. And on the ID and IQ plane, we have that circle. So the currents in the machine must be always within that circle. All right, ID values and IQ values must not go higher or outside the circle. And the voltage equation, remember, is an ellipse, all right? But as the speed goes up, the ellipses become smaller and smaller, all right? And at infinite speed, those shrinking ellipse comes to a point on the negative ID axis, okay? This point is called the characteristic point, all right? And that point is given by lambda PM divided by LD. If you go to the previous slide, you can see that if ID, negative ID times LD cancels that flux, then lambda D becomes 0. All right. So that's the limiting ID, all right, which is called the characteristic current, at which IQ is 0 and ID is the limiting value, all right. And if it is on the, go to the circle diagram, ellipse diagram again. Next slide. Next one. Yes. If the ID equal to ISM happen, then that would be this point, all right? Because the diameter of this is ISM. All right, remember ID square plus IQ square equal to IS square. So ISM is the diameter of the circle. It refers to the diameter of the circle. So if ID, or if this point comes here, that would be the case where the circle has shrunk to 0. So that means the machine will produce max infinite speed. The speed would be infinity, where the circle shrinks to a point here, okay? But if the circle shrinks to a point to the left of this point, then from this point, from the intersection of the ellipse, you are not seeing my arrow, right? you cannot see my arrow, the cursor. So that's one problem I'm having, that
Yeah,
if
we
I'm
can see.
not display, you can see my arrow?
Yes, yes. Yeah,
Moving?
we can see the cursor. Yeah.
Okay. So if we have the characteristic current somewhere to the right of that point, then the maximum, then the speed at that speed, from this speed onwards, we will have it, we will lose control over the machine, all right, because the torque, the ID and IQ could not be produced anymore, all right, from some equations which are coming next, all right. So what I'm trying to say is that if the characteristic point is right on the circle, then the machine can have very high field weakening range, all right. But of course, in some machine, the characteristic point is outside, but in most cases, the characteristic point is somewhat to the right of that intersection. If it is far to the right, then also we cannot reach very high speed. All right, our field weakening range will be limited. So the best arrangement is for the characteristic point to be very close to the intersection of the circle with the negative ID axis. Can I go to the next slide, please? Now, so what should be, in order to produce a certain torque, what should be the ID and IQ that references given to the current controller? All right. Now, if the machine is running at low speed, all right, lowest or below base speed. At base speed, the machine back EMF is amplitude is equal to the DC link voltage. All right, the inverter has a voltage supply, DC voltage. So if the back EMF is equal to the inverter DC supply voltage, then we cannot control the current properly through the machine because there is not enough voltage between the back EMF and the DC voltage supply to pump current into the machine. Okay, so if we are operating the machine below the rated back EMF, all right, then we can find the ID current from this equation. All right, this is simply an equation in which we do not, can you go back to the slide before the equation? The equation. Yeah. So if we are operating the machine at a speed for which the voltage is below the maximum voltage that the inverter can produce, which is determined by the DC link voltage supply to the inverter, then we don't need to consider this equation at all to determine the ID and IQ current range, okay, or current values, okay. So we simply know that this is below the the voltage in the Q axis and voltage on the D axis will be below VSM. All right. And that happens when the speed is below the rated back EMF. All right. So go back to the previous page where I had the ID calculation. Next slide. Next slide. Next one. Yeah. So when the machine is running at speed below base speed, all right, our current will always be less than ISM. That means we are operating within the circle. All right, back EMF is below base speed. So our current reference ID can be simply calculated from this equation. All right. Now, this equation is simply the equation which gives it, which is derived from there. Okay. Now, ID is given by this. All right. And IQ is given by this expression. Sorry, IQ is given by this expression, but we have found this expression is found from a condition that torque will be maximum. Okay, so under base speed, the condition for maximum torque is like this. So this is after a bit of a mathematical analysis, which I have not included for the sake of time. So anyway, so below base speed, ID and IQ will be related by this case, okay? Now, to produce maximum torque at a speed below base speed, we have to resort to this equation, all right? If we replace IQ by this equation, then our ID limit, the maximum value of ID becomes that, okay, to produce the maximum torque, okay? So, but because this condition is for maximum torque per ampere, and this limiting condition then gives you the ID current limit that would still produce maximum torque per ampere, okay? So this characteristic, if you plot the various values of, ID limit is that, so IQ limit would be that. So this, if you have ID value and you calculate IQ value from here, all right, and you produce maximum torque, so current limit for operation at any speed below base speed, the maximum current that ID current we could have is this, maximum IQ current you can have is that. So that will go to the next slide, please. Sorry, not that, the one before. The one before, this one. So the one, next one.
I think the slide 41.
After
41.
Yeah. So the red line here has combinations of during this for operation of the machine at below base speed, all right, depending on what torque you require, the operation of the motor to produce various torque will require various ID and IQ values, all right, along this line. Okay, and this is called the maximum torque per ampere line. All right. So if you operate the machine along this line, the machine produces a certain torque for which the minimum ID current and minimum IQ current will occur in the machine. All right. And if you want to produce the maximum torque at base speed, then your ID max would be that, and IQ max will be that. Okay. But below base speed, various ID IQ values will be along this line, but they will produce the maximum torque per ampere characteristic. So below base speed, the machine operates along this trajectory, and above base speed along this trajectory if the machine must accelerate at high speed to the required speed. And while the machine is accelerating to the required speed, the ellipses will gradually contract in diameter in radii, as shown from this to that, and even smaller, and so on. Okay. And if the machine is to stop acceleration and then run at a certain speed, it could be along the dotted line here. All right. After the acceleration is finished, it then operates along this line or operates along this line, depending on what is the load torque. Okay. So if the machine's limiting curve in terms of the ellipse is that one, all right, which means that the characteristic point is here, and the maximum speed that the machine can go up to is there, then it can only operate up to that speed and then along that. Okay. Depending on the torque. Now, if the machine needs to go to higher speed, then you can't, because that quantity in the square root, under the square root, in one of the equations before, will give you complex numbers. The quantity under the root over will become negative, so it will have no real value. All right. So from that to overcome that circumstance, we can move the control from voltage to maximum, from field weakening. All right. Field weakening, but with operation under maximum ID or NIQ. We are operating on field weakening because we were increasing the speed from there to there to there and so on, up to any point that we want to go to. Okay, but we cannot go beyond that because the quantity under the root becomes negative. So what we do then, we then go for a control called voltage limited maximum output trajectory, okay, which is called MTPV, maximum torque per volt. All right, the analysis for that is included further down. So if we do that, then we can run the machine along this trajectory up to this point, and then along this trajectory. All right, and then we can reach higher and higher speed. Now, most machines are designed, very high perform, good machines are designed to operate or to have the characteristics point very close to that. So this part of the operation doesn't, in most cases, is not required. But if the characteristic point is far to the left of this point, far to the right of this point, then maximum torque per voltage, which is along this trajectory, may be required. Okay, can I go to the next slide? Okay, so that's maximum torque per ampere trajectory. And in the following page, go to the following page, please. Okay, so in the field weakening region, we use the ID to reduce the field. Okay, remember that lambda D equal to LD ID plus lambda F. So if you make ID negative or more negative, then we reduce the lambda D, all right? So that will reduce the back EMF, and then the machine can run faster, all right? Because the ID current can increase and IQ current can also increase. Oh, sorry, IQ current can then decrease, all right? And ID current can increase. So that will increase the saliency torque or the torque or the reluctance torque, which is the second part of the torque equation. All right. So by making ID more negative, we can increase the torque and reduce the we can reduce the field, all right, so that the back EMF is reduced and then the speed increases, okay? But to make sure that we still produce the highest acceleration to speed above base speed, we make sure that ID and IQ current are at their limits, okay? So again, we do the same. We use the equation, which is, sorry, no, the previous slide, please. We again make use of the equation IS square less than ISM square, or stator maximum current square, which is equal to ID square IQ square. So we make the use of that in order to make the ID the limiting value. All right. So we put IQ equal to IS square minus ID. IS, if it is the limiting value, then IQ also is the limiting value. And ID is also the limiting value. All right. So we could put IQ in here, and then ID becomes the third equation from the top. All right. And if we then put the limit of current, all right, then it becomes the ID current limit, just as for the maximum torque per ampere operation. So during the field weakening, for fastest acceleration with maximum current values and maximum torque, we use these two current limits. All right. So there is a current controller and then the current limiter. If you go back to the block diagram, let's go back to the block diagram. Yeah, the block diagram. Yeah, there is one block diagram here, which is the IQ current limit and ID current limit. So the limit is indicated in the block diagram. So those limits are calculated according to this equation and placed there, okay? So this is a variable limit. One has to put that in the control system to execute the current limit. Okay, so let's go back to where we were. So the next slide. So once the current reference values are obtained, and they will be subject to limits as we have shown before. And then there is the current controller. All right, the Q-axis current controller and the D-axis current controller. And then there is some voltage compensation. All right, from the voltage equation, you should compensate the voltage according to what is these two equations are saying. From the after the current controller, GCQ and GCD, we have a voltage reference to go to the inverter, all right, to produce the voltage across the machine. But we should add to that voltage reference the additional voltage according to speed and currents as indicated by these two intermediate blocks. So that will enhance the voltage reference to produce the required current. All right. In other words, the current response would be more accurate and the current response would reach the reference value more quickly. So the control would be faster, more precise, and the torque response would be faster as well. Okay, so this is the way the motor is controlled. Okay, next slide, please. And then there is also some hierarchy in the control. Below base speed, that means when the VD and VQ are less than the sum of the D-axis and Q-axis voltage is less than the rated voltage of the machine or the maximum voltage of the machine, then we could then the stator IQ should determine the VQ, all right, first, and then the remaining voltage should be VD, all right. On the other hand, if the voltage has hit the limit, that means the back EMF has already been reached, then the ID current control should have the priority. So the VD would be selected first, and then VQ would be selected, whatever is the leftover, all right, which is in the block. I should have mentioned the block number, which is the right-hand side block, the second block from the top, all right. So if the machine is running above base speed, VD becomes selected first. The remaining voltage, available voltage, is VQ. On the other hand, if the rated back EMF has not been reached yet, the machine is operated at low speed, then VQ should be selected and VD should be selected. In fact, there is no hierarchy then because the voltage is not hitting the limit. Okay, so anyway, these are the hierarchies of control of VD and VQ depending on the speed at which the motor is running and whether the voltage limits have been hit. All right, next slide, please. So this is what I was talking about, the MTPV. where the quantity under the bracket previously did not become a positive quantity. All right, so its roots could not be found. So anyway, the analysis is given here, how to calculate the ID along that small trajectory that I indicated before, and how IQ trajectory is found. Okay, this more detail can be found in this paper that I have mentioned here. Now, can I go to the next slide? Yes, so this is the operation of the machine in simulation and experimentation. All right, the acceleration along the MTPA, then field weakening under maximum current, and then operation along the elliptical line to the final speed. All right, so sorry, go to the previous page, please. Previous page. So we can get operation over a wide speed range. All right, constant torque, and then field weakening. All right, and then this is the field weakening part. Okay, and this is constant torque operation. So all these trajectories have to be calculated online, and then or they can be stored in lookup tables, and the control system just finds the value from lookup tables or computes them, and then voltage compensation, and then the hierarchical selection of VD and VQ reference, and then that's it. So, and then that gives you very high performance control. Now, why high performance control? Go to the next slide now, please. Oh, so this is that MTPV that I was talking about for motors that have the characteristic point not very close to the intersection of the ID line, ID equal to IQ equal to 0 line, ID axis, and the current limiting circle. So if you use that MTPV algorithm, then your torque can be improved a bit, high speed torque. All right, but for most machines that the characteristic point is very close to the limit circle, so that may not be necessary. Okay, next slide, please. Now, this is another method of control called direct torque control, where the machine is operated with the torque and flux reference. Direct torque control I'm including in this presentation only to show that there is an alternative way of control, but most electric vehicles used the method that is I have already explained with the help of the rotor position sensor and control in the DQ reference frame. All right. Vehicle manufacturers prefer that because the sensor on the rotor gives them some confidence that control is always, the vehicle is always under control. All right, even at very low speed. Direct torque control is another way of controlling a synchronous machine, PM synchronous machine, because it in which the torque and flux are computed, and then those are used in feedback loops. All right. After all, in any control system of a motor, we are controlling torque and flux. So if we can close the loop on torque and flux, why use current loops? That is the question. But you need, in order to calculate torque and flux, you need currents anyway. So current sensors will be there, but in order to calculate or estimate torque and flux, you don't need position. All right, because position can be, as you can see here, flux is computed by voltage and current. All right, and torque is computed by currents and fluxes. All right, this lambda alpha, lambda beta, these are not determined by position at all. So if we can calculate torque and flux, then that's all we need. We don't need to, we need position. So direct torque control is a control method that doesn't require position sensor. And that's one component out of the system. And in some cases, it could make the drive cheaper. But we can calculate torque and flux and control the motor. Now, there are various types of direct torque control, but for vehicle, we need torque control as well as flux control. So there is a technique called direct torque and flux control, DTFC, all right, where the torque control loop and flux control loop on the left produces the V alpha and V beta voltage references, which then go to the inverter to produce the switching of the inverter, okay? When we have V alpha and V beta, we can use SVM, which is called space vector modulation, and it can operate at a constant switching frequency. Now, this technique was initially produced in our lab in our university, but subsequently it has also been developed elsewhere. Can we go to the next slide, please? Now, when you have direct torque and flux control, you don't have ID and IQ quantities, all right? So we calculate the stator flux and we calculate the torque, all right? And based on that, we can calculate the torque reference and flux reference, all right? The flux reference is the MTPA trajectory, sorry, the current limit trajectory, which was a circle previously, is this red diagram, all right? For every current on the circle, we can calculate the flux and the torque for every speed, all right? And that would give you this red line, which is not at all like a circle or an ellipse, okay? Now, the MTPA, maximum torque per ampere, is a trajectory like this on the stator flux versus torque plane, all right? So, and at the base speed, the ellipses that we had in the previous case, the ellipses become vertical straight line, all right? Ellipses are vertical straight line. So at the base speed, omega-1, the intersection of the MTPA and the current limit and the voltage limit trajectory, that's the base speed. So current limit trajectory goes through the intersection point. So below base speed, operation is along this trajectory. Torque and flux reference must follow this line. And this line can be saved in a lookup table. And then once the machine goes above base speed, then torque reference and flux reference follow this line to produce the maximum acceleration. All right. And if at any speed the machine has reached the final speed, then it comes down along vertical line towards this line and then along this trajectory. All right. If the operating torque is even lower. Okay. So this is the characteristic. This is how we obtain the torque and stator flux reference signal. All right. This can be computed from the data of the DQ axis based control, the RFOC based control. This can also be computed and saved in memory. And then we can follow the trajectories by simply generating the torque and flux references. And then according to torque and flux, the two hysteresis controllers produce the V alpha and V beta references, and then that drives the inverter. Okay, so the control is far more simpler, and the load on the controller is much more simpler if you are using trajectory stored in lookup table. All right, so let's go to some right here. So you can see that the machine was accelerated with constant torque and then reached the limit of MTPA. That means the base speed here. And thereafter, the machine is operated under flux weakening, so which is the parabolic line. And then at maximum speed, the machine then follows the vertical line and then the machine settles at a final speed. Okay, and the operation is along the vertical line then. So this is how the machine is operated. Accelerated to operated with maximum torque to base speed, and thereafter maximum torque production, but with CPSR trajectory following maximum torque, under current limit, but producing the highest acceleration under current limit. All right, but under torque and flux reference, according to what we have seen in the previous page, but operation along this line gives operation along with current limit and maximum torque. All right, for that speed. So this is how DTFC operates. It's very robust and very simple to do compared to the RFOC, which needs quite a bit of closed loop control and so on, and fine tuning of the controller and limit setting. Okay, next slide, please. Next slide. I think for this, because we are now, on my watch, it is about 12:15. So these are various ways of calculating the torque and flux. All right. In that previous slide, we showed you a way to calculate torque and flux, but that is very simple algorithm. Here we have a more accurate algorithm for estimating torque and flux, state of flux linkage. And this is a adaptive sliding mode observer for torque and flux. All right. These are available in some of the papers that we have written. I forgot to include the reference here, but if anybody is interested, I can send those papers. So go to the next slide, please. I'll finish it next. I want to finish it in a short time. So that's the trajectory following in experiment. Okay. Along the maximum torque per ampere trajectory, then acceleration along the limit circle, all right, or with constant current, but with flux reduced, all right, and torque reduced accordingly. So the product of torque and speed remains constant, and then finally settling at the final speed. Okay. Now this control is also very mature, like the RFOC. Next slide, please. So this is just showing how good the sliding mode observer for torque and flux can be, all right? And it also has a position estimation and speed error for the speed controller for closing the speed loop. All right, so you can see that the speed error is very small. So what we obtain as speed feedback without the speed sensor or position sensor, we can still get very good or accurate speed sensing. So that speed control loop operates very well. Okay, next slide, please. So this part is about parameter dependence of RFOC and DTFC. In the previous slides, in all our mathematical model, we have calculated ID limits, IQ limits, or torque reference and flux reference, but all of those formulas had machine parameters like resistance, inductance, flux linkage, and so on. But those parameters in a real machine change with temperature and change with current. So we should adjust those parameters in real time. All right. The resistance parameter and the flux change and the flux lambda F change due to temperature of the magnets. Those are slow processes and therefore can be observed by many recursive observer techniques. But the inductance change of the machine takes place with change of current. So if ID and IQ changes suddenly, as happens during acceleration and deceleration, we also need to, it would be good if we could compensate for changes in those inductance parameters. Now, LQ changes significantly for IPMSM. LD does not change significantly. Okay, but LQ can change by up to 30%. So it can change the torque estimation or current estimations or the current limit calculations quite significantly. Next slide, please. Next slide.
Excuse me, sir. Yeah, so due to the time constraints and all, yeah, can we skip the part 3, sir? would it be, since it's also like,
Okay, yeah, I can
yeah,
skip this part. These are quite advanced
yeah,
and not yet, these techniques have not yet gone into electric vehicles. Right? These are very recent techniques,
yeah,
not part of any electric vehicle yet. All right. So I can skip this part. Thank you for that. All right.
yes, if I accept
If you are
it.
interested, you can read this last few pages in my presentation material. Thank you
Yes.
for listening.
Yeah, so even in the upcoming workshop series, since it's advanced thing, we can have that part in the lecture series, since it's advanced one for the participants. Yes, we like to have that one
Okay.
also in the future. Thank you, sir.
Okay. Okay. All right. So are there any other questions
Um,
from the
I think,
audience?
yeah. So, Professor, I think thank you so much for taking a lot of time. Even you have passed your midnight. Unfortunately, we had few, like technical issues coming here and there, but that always happens. That's all fine, I guess. But it was a wonderful session. Thank you very much. So I'll let all the formalities to be done by the other young professionals. But I have like very a generic question for you, not very high theoretical question from the things that you have explained. So basically,
Yeah.
now you have explained a lot about the electrical vehicle technology and all. So in my according to my knowledge, I have seen like before these electrical vehicles being popularized. So we knew that for a long time the locomotive engines have been using electric power to run them. I have seen like two ways. One is like even in Sri Lanka, I mean, in Sri Lanka, we don't have direct electric locomotive engines for the train. But still, I think even they use diesel engines. Within that, I heard that they convert the the diesel engine actually runs a dynamo and then generates that electricity inside and then run the locomotive engines are actually run by electric motors. That is one part. And from the other side, especially in India, a country like India, they are running lots of locomotive engines from electricity. Like I think most of their locomotive engines are running in electricity. So that is one thing. And I think recently they have introduced this Vande Bharat like high-speed trains. They are not as much speed as bullet trains, but they're very close. And then we have in Japan and China and various places, we have bullet trains a lot. And so that is another application. And then we see in a lot of modern cities nowadays, we see these metros, which also uses the electric method of vehicles. So can you like very briefly explain like what are the specific differences in between these and then the electric vehicles that you were talking about, like normal electric vehicles?
The electric vehicle trains, like currently diesel engine will use a generator to produce electricity, all right, across a capacitor or a mostly capacitor or a battery, and then the engine, sorry, the train will be run by electric motors, okay? But the dynamics of electric trains are not very high. You don't need to have very fast acceleration or fast braking and so on. Okay, the dynamics of control of those machines driving electric trains are quite slow. All right. So control using DQ theory is not needed there.
Right.
All right, simple VF control, variable frequency control will be okay. However, for electric vehicles, which are on the road on your streets, you need to have very fast dynamics. All right, sudden braking, sudden acceleration, sudden slowdown.
Yeah.
All right.
Yeah.
And so for that, you need very sophisticated control, like what we have discussed today.
Right.
Okay. And we are now also heading towards autonomous vehicles, autonomous driving, driverless driving. So you need to have very fast decision making and very fast control. Trains don't need that.
Right. Right.
Okay.
Right.
So that's the difference.
Right.
On-road vehicles will be driven by very fast dynamics. So that's why you need RFOC or DTFC.
Right. Yeah, that's
All
pretty
right.
clear. I think that's the main difference. I can understand. Yeah. Yeah. Nice.
All right.
Yeah. All right.
Question?
Audience, like anyone else has, if you have any questions, you can quickly raise them.
So if you have any questions, you can raise them via the chat box, or you can unmute yourselves and direct the questions to the professor.
Yes, you can give them my my email address, and they can send the questions to me. Okay.
Yeah, that could also be. Yeah. So maybe like we can collect any questions that they have and directly send to you so that you
Or they
clarify
can
it.
send the questions to you, and you
Like,
can then send it to me.
yeah, yeah. Either way is fine. And then during the workshop series, maybe we can have more similar sessions.
Right. Anything else? Anybody want to ask any more questions?
It seems like there are no more questions. So shall we proceed? Yes,
Yeah.
we have. Yeah. Before we close, we would like to take a group photo to commemorate this event. So I kindly request all attendees to turn on their cameras for a moment. Please smile and stay on camera for a few moments while we capture this memory. Savindu, are you ready to click the photo?
Yeah, I'm ready.
Yeah. All right, everyone. So if it's
Okay. I'd like
possible,
to receive
please switch on your
of all those
cameras.
of that. I'd like to receive a copy of that
Sure.
group photo.
I will share it with you, Professor. We'll do it.
All right.
Yeah.
I hope the talk has been informative for you.
Absolutely. Like,
because it was so late, my voice got a bit tired.
right. We understand. Like, thank you. Yeah, we should really appreciate your commitment, like staying late night and delivering this speech. I mean, we know like to gather more audience from our side, Sri Lankan side, like we wanted to have it in the evening, but we knew that it will be a bit too late for you, but still, thank you for accepting that one and bear with us having this time. Yeah, thank you.
Okay. All right. Thank you. Bye.
All right. It seems like these are the people who have switched on the camera. So, all right, everyone. I'll count from 1 to 3, and then use my. Here we go. 1, 2, 3. Cheese. Are we good to go with the photos of it?
Yeah.
Yeah.
Yeah, thank you. You can switch off your cameras. Dear Professor Rahman, we are deeply grateful for your enlightening session today. Your insights and expertise have been invaluable to all of us. Thank you for sharing your knowledge and taking the time to be with us. Your dedication and passion for the subject have truly inspired us, and we feel privileged to have learned from you. And your ability to convey complex concepts with such clarity is commendable. And we appreciate the effort you put into making this session both informative and engaging. Professor Rahman, we would be grateful if you could accept this token of appreciation as a small gesture of our immense gratitude. Thank you once again for your invaluable contribution to our learning journey. Yeah, thank you, sir. As we come to the end of our session, I would like to invite Ms. Dushinta Ramalingam, IEEE Y2N Pro Chair, to deliver the vote of thanks. Over to you, Ms. Dushinta.
Can you hear me?
Yes.
You're audible.
Yeah, okay. So, good evening, everyone. As we draw this insightful session to a close, it's my privilege to deliver the vote of thanks. On behalf of Y2N Pro of IEEE Young Professional Sri Lanka, I would like to express our sincere gratitude to everyone who made this event possible. First and foremost, our heartfelt thanks goes to Professor Faz Rahman for his outstanding keynote presentation. Your detailed exploration of the evolution of interior PM synchronous machines and control techniques for electric vehicle applications has been both enlightening and inspiring. Your expertise and dedication to advancing knowledge in this field are truly commendable. And we are grateful for the time and effort you have invested in sharing your insights with us today. We would also like to extend our special thanks to Mr. Kavingopul Ekanayaka, Chair of IEEE Industrial Electronics Society, Sri Lanka Chapter, and Dr. Akila Vijayatunga, Chair of IEEE Power and Energy Society, Sri Lanka Chapter, for their continuous support. Your collaboration and support have been instrumental in making this event a success. We appreciate your commitment to fostering knowledge sharing and professional development within our community. A special note of thanks to IEEE Industrial Electronics Society Distinguished Lecturer Program for providing us an opportunity to deliver such an awareness session to the young members on advancements in electric vehicles. We extend our gratitude to the Executive Committee of IEEE Young Professional Sri Lanka for their continuous support and encouragement. I would like to appreciate the organizing committee of Y2N Pro. Your hard work and meticulous planning have ensured the smooth execution of this event. A heartfelt thank you to all our attendees. Your active participation and engagement have made this session lovely and enriching. Thank you for your thoughtful questions and for joining us on this learning journey. As we conclude, I encourage everyone to stay connected with IEEE Young to Niche Professionals for more such informative and engaging sessions. Together, we can continue to learn, grow, and make significant strides in our professional journey. Thank you once again, and we look forward to seeing you at our future events. Have a great evening. Thanks. Thank you, Patam.
Thank you, Ms. Dushinta. Before we end, please take a moment to fill out the feedback form by scanning the provided QR code. Your feedback is crucial to us, and we would love to hear your comments and suggestions to help us improve and deliver more valuable sessions tailored to your needs. Thank you once again for your participation and for helping us make our sessions even better. Additionally, you can join our WhatsApp group by scanning the QR code. We are planning a series of workshops and events in the coming months, and this group will be a special community for EV enthusiasts like yourself. Thank you everyone for your participation. Special thanks to Professor Faz Rahman for his enlightening session. A big thank you to all the organizers from IEEE Young Professionals Sri Lanka, IEEE Industrial Electronic Society Sri Lanka Chapter, and IEEE Power and Energy Society Sri Lanka Chapter for their hard work and dedication in putting this event together. We look forward to seeing you at our future sessions and workshops. Have a great evening, everyone. Stay tuned for more exciting events from IEEE Y2N Pro. Good night. Stay safe.
Thank you very much.
Thank you. Thank you for attending my talk. Thanks to all of